Carbon fiber composites and manufactured by fiber placement processes have been state-of-the-art in aerospace industry for more than 2 decades. It allows an optimal alignment of the fibers with the load and stress paths of the components. This morning's keynote speaker will dive into the latest material and process developments for the fiber placement technologies of tomorrow's aerospace industry. Please help me welcome Executive Vice President and General Manager of Composites, Fibers, and Materials, SGL Carbon, Andreas Willner.
Okay, good morning, everyone. Thank you for the introduction, Mike. I'm happy to be here and to talk to you about the latest advancements in fiber placement. Before we start, I'm curious because we have the panel afterwards as well, and since this is a manufacturing conference, maybe those who are dealing with carbon fibers or composites in general in their work life, please raise a hand. Are there? Wow, that's many more than I had expected, and makes me feel happy. So that I'm not talking only to people converting metals here, but some people who are dealing with carbon fibers or glass fiber composites. It's an honor to be here again talking. I did that a few years ago, and the last time I talked here, I spoke about basically the transition, what we as SGL Carbon can take from the automotive industry, where we have a strong presence in, and deliver it to the aerospace industry. That was basically on thermoset materials, fabrics, and highly automated processes for the BMW supply chain, and how we can further develop this for future commercial aircraft applications and make use out of that. When you do that, you encounter real fast that there are some issues, and those issues are you're always depending on the process, wasting a lot of material, and especially when you use carbon fibers, it really gets difficult and basically makes the process or the product at the end of the day so expensive that you are not competitive with standard solutions. And hence we had been really digging deeper into fiber placement, and that's and all the advancements over the last years. Few words on SGL Carbon and us before I'll dive into this topic. What sets us apart from our perspective? Since we believe that it's really important not to have just carbon fibers in-house and the materials, be it textiles, thermoset, thermoplastics, you also have to have the component capabilities and the capabilities to manufacture in high series volumes. That's important. You cannot just throw a material over the fence and somebody will pick it up and make a part of it. This won't work. That's something we have experienced, have learned over the last years. We have large volume carbon fiber capabilities. We are among the top 5 carbon fiber producers in the world. We have the engineering and development capabilities in place to develop materials and processes, but do also the engineering work to come to a solution for our customers. And what we have, and that's something we are really proud of, we prove it daily that we are capable of manufacturing parts in series. And the part you see here, that's the leaf spring, and we're manufacturing for customers more than 500,000 of such springs in standardized manufacturing cells per year. So that's really serious application. SGL Carbon, our business unit, our division, we have a global footprint, and as I said before, that starts with the fibers, or it starts with the precursor. Those are our precursor sites. Then we convert those into carbon fibers in Beaufort, Scotland, Moses Lake, Washington State. The plant we started up in 2012. At that time, still with BMW. Now our plant, and from there, our fibers and also glass fibers are converted in the red dots into materials, and then either sold or converted into parts. In the US, we do have a foothold of 3 sites, one here in Gardena, another one in, as I said before, in Moses Lake, and in Arkadelphia. And we will grow this footprint. So that's also a reason for our participation here. So we want to grow in the United States. We are currently $500 million sales, US dollar sales business unit of SGL Carbon. Okay, let's dive into the materials now. When you talk about composite components, when you talk about fiber reinforced plastic, it's always a combination of the materials, of the process, and the engineering. And you have to have all of these in place, otherwise it won't work, and you have to select the appropriate ones. The materials you see here are parts of our dry textiles toolbox. We always try to develop standardized toolboxes, because otherwise it gets too complicated for us and for our customers. And hence we have started to develop this toolbox, starting with fabrics, non-crimp fabrics, woven fabrics, most cases thermoset. For thermoset applications, we have developed a so-called fixed toe material, which we will see later. That is a material we have developed for thermoset fiber placement applications, non-wovens, which also go into fiber placement, and of course stacks, braidings, and preforms, and we will see those also later on, especially the braidings, which will play a role in future as well. That was basically the starting point for us, and from there we developed the thermoset material toolbox, which is, well, when it comes to prepregs, of course, state of the art. But we took this and developed, based on the prepreg technology, toe pregs, which are not a slit tape, but we take basically a carbon fiber, we impregnate it right from the beginning, and re-spool it, and make a toe preg out of this, which then is used for fiber placement processes. In addition to that, we also have pre-impregnated carbon fiber non-wovens. Those materials stem from the supply chain we have for the automotive industry, and those are basically off-cut materials we take and make non-wovens from those. And then we have stacks, and stacks are basically multiple plies of material we put on top of each other, trying to minimize waste right from the beginning, and which then can be put into fiber placement machinery and further reinforced. Okay, there comes the thermoplastics. Our thermoplastic material toolbox is based on, we take a carbon fiber. We take this carbon fiber and impregnate it with either polyamide or polypropylene. Take those rods and take multiple rods and make either from those rods profiles or tapes or sheets, or we also make customized organelle sheets. And the UD tapes go into fiber placement applications as well. So that's another material class we have developed for fiber placement applications. And those are all the basis for fiber placement. So you have to have in place such standardized materials, because otherwise it gets too complicated and you lose sight basically on what you're doing. As I had said before, for applications where you have one part, large volumes, there are already processes out there. We have those in-house, but when it comes to smaller quantities, much more complex geometries, it gets more difficult, and the waste increases exponentially, and that is really the critical thing with all the applications. We can compete with our materials, be it glass fiber, be it carbon fiber, be it hybrid materials. We can compete when we minimize the waste. And this is, for example, the case with such glass fiber reinforced plastic leaf spring applications. But when it comes to complex geometries, small volumes, it's totally different. And to give you an example for that, that's an example taken from a real-life project we had in the past with a large German automaker. They kept the solution. They started with a steel solution, and then they wanted to have a lighter solution, and ultimately, because of cost, they ended up with this aluminum solution. However, we went through various iterations, and those involved fiber placement technologies, and that was basically the starting point for our efforts to think more about fiber placement than we did in the past. As I had said before, we came from large volume, large parts, either made from wet pressing or high pressure RTM, complex tool geometries, expensive tools, a lot of waste, and we wanted to reduce that. And so I had to start thinking about what can be done. And in the first iteration, well, that was the simple approach: make everything from carbon fibers in the way we did that for other applications. But when you look at it, you save a lot of weight, which is great. But when you look at the cost, you triple cost of the now series solution, which is of course not acceptable for the OEM. Then we looked at it in the next iteration step, and that gives you a feel for the competencies you have to have. You have to have the material competencies, and you have to have the engineering competencies in-house to go through this. And we looked at that. We came up with a hybrid solution with a core, 50% carbon fiber, 50% glass fiber. But this was still too expensive. And the next step was to get rid of the core and make more use of carbon fibers in some specific regions of the part, look at the load pass, and minimize waste again of carbon fibers, but really make the most out of it, make most out of the carbon fibers. And you couldn't have done that with standard processes. And that is a way of thinking. We believe that combining multiple materials and also technologies. So this is a combination of non-crimp fabrics, glass fibers with fiber placement on top of this. And this is something that saves you weight and also reduces cost. So that's a good approach, but it's very complex and very complicated, and you have to accomplish this. When you look at the cost targets and what is basically what you see here is the cost per part, and that's for this part. It's a steel part. It's even lower than, of course, the cost of the aluminum part. Of course, weight goes down significantly. That's on this axis here, what you see at this curve. This is basically what I've called here state of the art. State of the art is a standard approach of using carbon fibers here, making everything out of carbon fibers. But when you compare, of course, the cost, it doesn't work out. And with several iterations, you lose some properties, but it's still good enough, and you end up with such a hybrid solution with fiber placement. So that's a good example of how we think and what we want to bring to the aerospace industry as well. That thinking that we can combine here several materials and not only for huge structures as it had been done with fiber placement in the past, but do local reinforcements as well. And why is this important? When you look at what is happening here, as I said before, the last time I talked about what is happening to commercial aircraft and how we could utilize what we are doing within SGL Carbon in future aircraft to replace our autoclave processes and to make, for example, wing structures with out of the autoclave infusion processes. But in future, when you look at the developments here, you see that the unmanned aircraft systems are systems which will outnumber commercial aircraft on a global basis real soon. And well, now only in or most applications in defense applications, but in future as well in commercial applications. And when you look at how what such air taxis, for example, look like, you will see that it's not such unmanned aircraft systems don't have huge structures, huge flat parts. Such parts are round parts. You have a lot of curvatures. You have, for example, when you look at the doors, a lot of glass. However, you have to reinforce that, and hence you are not able to do something there with standard approaches like we did in the automotive industry. You would have a lot of waste here, and that would make such parts so expensive nobody would utilize fiber reinforced plastics here. And for example, when you look at these parts here, those could be made from bradings. You could have here fiber placement for such structures at the doors. So there are multiple areas for such air taxis where carbon fiber reinforcement with fiber placement processes may be utilized in future. Hence, we think this is really a technology with the further developments we are going into that should be used in future. And when you look at the different applications here in mobility, in communications, in defense, surveillance, and agriculture, the variety of such drones, unmanned aircraft systems is so huge that you do not talk about huge volumes always. You talk about limited numbers, maybe hundreds, thousands of aircraft, but that would not allow for very expensive toolings. Hence, you have a huge advantage here with fiber placement technologies. When you look at, once again, to give you a little bit more insight into what happens with the state-of-the-art carbon fiber or glass fiber processes. When you have a fiber, be it a carbon fiber, for example, you manufacture either a woven or a non-crimp fabric, and then you make those stacks out of those, you preform it, and then you put those into a huge RTM press. The equipment is expensive, the preforming equipment is expensive, the huge RTM press is expensive, the tools are expensive, and then you go into finishing operation, and this application shows here how the glass fiber is made. Those are either you have separate you have the separate cavities, and then you have to separate those from each other. But this is really standardized, high series, not a lot of variation in there. When you want to have solutions for smaller volumes and just local reinforcements, then you have to go through a different route, and that's what we are showing here. You have to have either here our automated fiber placement processes or another process which we call freeform winding. You take a tow preg and wind with a robot the specific geometry. So this is these are specific processes which use our tow prags here, and the tow prags is a thermo set resin system, and you make the part, and afterwards you cure it. It's a fast cure resin system. You don't need the expensive high pressure RTM molds. You save a lot of money in that regard. And with the tow prag, because of the process here, when you impregnate the fiber and don't have a back paper on the tow prag, you save money there as well. And it's a very nice process and a nice material for those two processes here. However, here you see the standard process, which is state-of-the-art with pre-prags and pick-and-place operations, autoclave technologies. So we believe that this here is the future for applications as we have seen before. And when you look at it here at this setup, that manufacturing setup, you see here, it is much easier, much simpler. You have the fiber placement equipment. You take this either the UD tapes or the tow prags. You lay up the parts. What you see here, you have those parts where you save, where you don't waste the material, which is really important. You don't have a a stack where you waste maybe 80% of the material afterwards. You lay up the fibers where the fibers are needed. And then you have a simple press, which is standard state-of-the-art technology. You don't have to deal with high pressure resin transfer molding, which is very complicated, and so that makes it a lot easier here. And when you summarize the advantages of the technology here, it's really the high layup rate. So the parts I have shown you, those parts can be manufactured below 10 minutes or so. That's relatively fast for such parts. The backrest, for example, of a car with high precision. When you pick the right process, the right material technology, it gets economical, but that's a prerequisite. You have to pick the right processes and the right materials. It's ideal for complex structures. It can be 2.5D. It can be really a complex 3D structure with inserts, with metals. So you can have various materials and parts integrated into such a fiber placement component. Of course, it's load path optimized, and that's what it's really about. Make use of carbon fibers where it makes sense. You minimize the waste, and I've said that multiple times, but that's really the most important thing. You have the opportunity to do hybrid material layup, combining even metals or glass fibers, carbon fibers. And of course, the accuracy of the placement is very good, the repeatability, and you can, of course, log all the information. You have the history available when it comes to virtual processes. Now I show you a movie on what we do in our fiber placement center.
That is, automated, load path optimized, material efficient layup and cutting of fibers, plays a key role in industrial mass production. To incorporate this technology into more high-volume applications across industries, SGL Carbon and Fraunhofer IGCV founded the Joint Fiber Placement Center, with multiple locations in Bavaria, Germany. With different high-tech machines, our customers can develop production concepts for fiber placement technologies. It's been specially developed for mass production, the CNC-controlled Stax Compact 1700. The machine enables toe pegs and thermoplastic tapes to be automatically and reproducibly routed away from the spool, very close to the desired final contour. The FiberForge Relay 2000 is a tape-laying system for advanced thermoplastic composites. The system allows for different material combinations and widths, and manufactures tailored stacks highly productively. For the layup of thermoplastic tapes, the Compositance RoboMag is a robot-based machine. The material is only fixed on the edges of the part geometry, enabling fast processing speeds and high layup rates. This machine enables multi-material processing of thermoplastic tapes, toe pegs, and dry fibers. The Coriolis Composites C1. It is suitable for 2 and 3D part geometries and features load path optimized layup of composite components. the Fiber Placement Center, developing solutions for innovative manufacturing.
When we started to, or let's say in 2016, we started to think about setting up something like the Fiber Placement Center. And we did that because we became aware of the challenges here. And the challenges were really selecting the appropriate material and doing all the engineering work, doing the in-process process control, doing the programming side, the CAD/CAM. All of this was quite challenging, and we felt that there are quite a few innovative solutions out there, but when you go to one of the machine suppliers, you get one solution, and of course this solution is being marketed as the most appropriate solution. However, that's not the case, and hence we said together with Fraunhofer IGCV, it may make sense to form an alliance here and really get all the existing technologies, combine those, and give our customers, our partners, the opportunity to look at such technologies and compare the technologies, the competing technologies, and learn from us how they can find a solution for their specific challenge. And that was the idea behind the Fiber Placement Center, which we announced last year at the JEC show in Paris, and then had the inauguration event last year in the fall in Bavaria. And what you see here is are some of the machinery and equipment you had seen in a video before, and we are adding more. I think by the end of the year we will have 9 different technologies in-house, either at our site or in Meidingen or in nearby site in Augsburg or Taufkirchen. And what is really amazing here is when you look at the layup rates, you come from high layup rates where you can make a part in maybe 3 minutes or so, and you come down to much bigger parts, as you may know, for example, the Coriolis equipment, which is quite familiar in aircraft, in the aerospace industry, and you have basically many of those machines which can either use thermoplastic, thermoset materials, or even dry textiles. And so that is really mind-boggling. And think about as a user, you have to make a decision which equipment to choose. It's really difficult, and that is the reason why we said it makes a lot of sense to bundle our competencies here and to offer this to the customers. This is really, we believe, a good approach to demonstrate how fiber placement can be used in future, and in particular in applications like the aerospace industry with unmanned aircraft systems. Of course, you may not forget about the engineering process chain, which is very challenging as well. How do you get from a part design to basically the layup pattern? And that is very challenging since most of the equipment suppliers offer their specific solutions, but those are proprietary solutions. And that is, of course, that's definitely a challenge for the future to come up with more standardized solutions there in order to not only have the virtual chain, but also have it in reality then. That's that's something you have to manage. You have to do the entire design and engineering process. And we believe that you have to master 3 different parts of the equation. That is, of course, the material toolboxes. Hence, we have set up the textile, the thermoset, the thermoplastic toolboxes. You have to add the engineering competency, really coming from the concept study, going through product design, the analysis, the prototyping, product testing, and you have to have the component processes in place. These are processes we have in our Lightweight and Application Center, and here such processes in the Fiber Placement Center. And you have to do this in order to meet the requirements. The requirements are, as I had said before, if needed, mass production, of course, automated production, and hybrid design. Use carbon fiber only where it makes sense, and do not get overboard with the use of carbon fiber. Mix it with glass fiber, mix it with other materials, do load pass adapted design, and minimize, of course, scrap and waste. And when you do this, then you can come to very fast solutions, and in some cases even come down to this 3-minute takt time here for some applications. However, I strongly believe that fiber placement is a key technology for the future, and with innovative materials like Taupreg or new thermoplastic materials, this is a good basis. And with all the different machinery and equipment which is currently being developed, it is really challenging when you look at the vast amount, at the mind-boggling amount of solutions, of processes out there. And if I were in the shoes of a user, I would be confused, and making a selection is really difficult. So I believe that is one of the biggest challenges, really, to pick the appropriate equipment, to pick the appropriate process. Another thing is the design process, which requires virtual development tools, which are not yet standard. That's another challenge to automated fiber placement, to a higher penetration of fiber placement. And of course, integrating all these new technologies into the existing digital landscape in an enterprise. That is something which is also quite challenging because of their proprietary programming software packages to come up, for example, with a CAM program. With the code to lay up the part. These are all solutions which you have to implement in parallel to the already existing solutions. Yeah, that's it. What we believe are the challenges to high-rate fiber placement. However, we think that this is a very promising technology which goes beyond the standard state-of-the-art use of pre-preg in large structures. And I'm looking forward to questions which I'm happy to answer now. Thank you.